Okay, guys, we're all set. Okay, listen up. Shay, why don't you kick us off by reading out the introduction here?
Introduction. We've already learned the basics about gravity, that all objects that have mass are attracted to all other objects that have mass, and that gravity is one of the four fundamental forces of nature. However, we have only mathematically worked with the force due to gravity acting on objects on the surface of the Earth. At this distance from the center of the Earth, all objects experience a force of
9.81 newtons per kilogram.
Yeah. This value is a constant, which only exists on our planet. If we want to determine the force due to gravity experienced by any two masses, the math gets a little trickier because there are more variables.
There you go. Okay, yeah.
So when, say NASA or whoever is looking for an equivalent planet like Earth,
Yeah.
in terms of size, would they just measure the gravity?
Well, there's a range that, I mean, if you colonize another planet, you'd have to take into consideration the change in bone structure that would occur if you had like a 10% difference in the gravitational constant, either more or less.
8% difference would actually affect.
Yeah, it would affect a lot of things. It would take probably a few generations for us to adapt. Yeah.
Change in bone structure? So
Oh yeah, your
gravity.
bone. If you increase force of gravity, your bone density would get higher, muscle strength would get higher, everything. Yeah.
That's the reason all
Yeah.
evolved. Logically,
Isn't that
like
what-
Superman
that's
can
Superman's
fly.
Yeah,
we're not getting into
Can jump like super high on the rock.
Stay focused here, boys and girls. Stay focused. Okay. Since gravity exists between any objects with mass, it makes sense that the amount of mass that comprises an object has an influence on the amount of gravitational force that the object is able to exert. To be specific, the force of gravity between any two masses is directly proportional to the size of the masses. Mathematically, so if you have two rocks and you want to double the force of gravity between them, if you double one of the masses of the rocks, then you double the force of gravity. If you double the mass of both rocks, then you quadruple the force of gravity. Secondly, since gravity expands outwards radially, like a ballooning sphere, since the surface area of the sphere increases as a function of r squared, the concentration of gravity decreases at the same rate. Now, expressing gravity as a concentration it's not really what it is, but if you have a finite number of arrows leaving a single sphere, okay, and you actually count the number of dots at those arrows where they pierce the surface of the sphere. If you think of those finite number of arrows and the concentration of the dots as they pierce through the sphere, as the sphere gets bigger, it's a function of 1 over r squared. Okay, so as you double the radius of the balloon or whatever, the sphere, then you quadruple the surface area of it. Okay. Yeah.
What happens if the mass is not spherical?
Then it just gets more complicated. Again, that gets into you have to integrate the shape of the object. Okay. Concentration of gravity. So mathematically, Fg is inversely proportional to radius squared. Finally, while the force of gravity acting between two objects is proportional to each object's mass, this linear proportionality has an extremely small slope because gravity is such a weak force. The value that scales down the slope, and it's capital G now, is called the universal gravitational constant. Universal gravitational constant. Yeah.
This is not really important, but shouldn't 1/r2 be r to the -2?
Yeah,
So
sure.
it's just how we do the ideal one. It's the same.
Good call. And G equals 6.67 times 10 to the power of, what do you think?
Negative 11.
Negative, oh, I'm reading it off the calculator. Negative 11.
Oh, you haven't.
And that's the unit, and that is Newton meter squared per kilogram squared. And let me show you why.
Wait, kilogram, per kilogram squared, true.
Just a side note, you don't have to copy this down if you don't want. Unit is neutral. Oh, first let's put the whole equation together first. Okay, so force of gravity is proportional to both masses, inversely proportional to r squared, and scaled down by a factor of g. And that's the whole equation right there. Now, the side note is explaining why that unit of g is the way it is. Yeah.
Did you design the
Yeah.
Can you next time not put the topic?
What?
At least some white space.
Sorry, yeah, this one's kind of packed. I know I didn't double space that one. Usually I make them bigger. Yeah. Can you live with it for today, Tom? Okay.
This is a big circle.
That's what has to go in to get. That's trust me, I'm gonna get it somewhere here.
To pull out the whole.
Is it a circle or a zero?
That's just a circle. So we have newtons on the left-hand side. We want newtons on the right-hand side. So this circle has to somehow cancel out meters squared in the denominator and kilograms squared in the numerator, and leave us newtons. All right. So the unit on G is literally just fudged in to cancel out all the other units. So the unit on G in here
Moles per liter seconds.
Then
What?
It's grade 12 chemistry ones. Yeah,
Okay.
just to cancel out. Okay, I see.
So literally, it's just to cancel out. It multiplies by meters in the numerator to cancel out meters squared in the denominator. Divides by kilograms squared in the to cancel out kilograms squared in the numerator, and then throws a newton in there
How in the world do you ever find out that it was 6
experimentally.
But what experiment?
It started off with I think it's called the Cavendish experiment. You know what? Let me show you. A picture's worth 1,000 words.
Yo,
Yeah.
is Cavendish in place?
Cavendish?
Sounds like one.
Coventry is. I'm not sure about Cavendish.
It's a street. So is Manchester. Do you know what else is? Well,
Yeah.
Okay.
Sorry, I just.
What's an easy one here? So this guy Cavendish, he set up in a very low pressure, like they tried to create a vacuum, as good of a vacuum as they could do whenever this was done, I think in the 1800s. He had two really heavy masses, and then he had two really light masses on the end of a very low friction, perfectly balanced torsional rod. Okay, and he measured the acceleration of the traction as the two masses were attracted to each other. Okay, and by measuring that rate of acceleration of the rotation of the bar, he was able to come up with a pretty good estimate. And then after that, like there's been revisions to that experiment. I don't know exactly how they came up with the modern value. I imagine it involves celestial measurements
And
instead
then
of
you'd be going,
terrestrial.
maybe like the acceleration inwards then? Would be,
Yeah, it would be the centripetal acceleration would be measured.
Is that what you're gonna do for hours on?
No,
yeah, that'd be
no, you
crazy,
need
man. How you
to
do that?
balance this is like such fine tuning. There's no way that you can do that.
You can
As
really
well.
respect that. That's surprising.
Is there a way to,
It would be pretty cool, but I mean,
we just get a few money?
the sources of error would be massive.
Exactly.
Hey,
Focus on it.
monkeys.
This class is really hyped today because it's after the bio exam.
Okay. Okay. First example.
Between the two buddies.
We need to see how far they are apart.
This rule has too many bad
Sorry.
team members. This rule has too many bad team members.
That's just
Four.
four? Who? You?
You're being surrounded.
Oh, so it's you, Megan, Kahir, and Abdul?
Yeah. You're being surrounded.
That's what happens. I get an email.
Was there
Michael
even
still
say
there?
teams use
Hello,
their
Michael.
words? Standing? Oh, you're just adding, okay. That
Yeah.
makes sense. I was gonna say.
You know what? I've done this note for about 2.5 years now, and I still haven't changed that example.
You could just put it
I just keep forgetting every day. Every time I do this, I keep saying, "Oh, I gotta go back and add that 2 meters apart." And I just keep forgetting.
What are we gonna do it now?
Question.
I will. I will after this class.
Yeah, like we
Grab
should
the
start
proportion
using.
for the two masses, right?
Yeah.
If they're two different masses.
You multiply them together.
Okay. Oh, I see. Two bodies.
I hate that. Every time I have to really
I'm assuming the textbook's probably gonna give us.
Don't be big. Unreal.
So you literally just plug it into the phone.
Yep. At this point, yeah.
A lot easier than that.
Guys, it's just example number
Don't worry,
one.
guys.
Just example one. That's right.
You're speaking.
Example 2, you'll know.
What is it saying?
Commercial.
No.
Now this is where brackets and all this fun stuff in your calculators becomes really important.
right. It should be 7.9 times 10 to the power of -8.
Sounds about right.
I got 7.8 times 10 to the negative
8? You mean 9?
8, yeah. I got 7.8 times 10 to the
I got 7.89.
Oh, hold on.
7.89.
Oh, yeah, same,
7.8.
yeah. Sorry, yeah. 7.9 times 10 to the negative 8.
Hold on, let me check. Step up.
7.9.
Yeah. We'll leave it at 7.9.
Which is believe it.
Goodbye.
Oh, that means where are we?
6, 7,
It's
8.
eight.
Sorry?
What'd you just say?
The bio.
Yeah, I think it's like 9.
Why does this not work?
Yeah, I know.
Am I just saying that?
No, because Tom just said to read it.
Oh, yeah, I know. What's weird? Yeah, like my cousin told me just drop it.
It doesn't.
Okay, any questions about that one?
I do, but it's not as reading here.
Next question.
Oh, yeah.
Yeah, forget it.
That's the next question, right?
Yeah.
Oh, no idea.
Things escalate quickly here.
Yeah, so
Oh,
so
my
this
God.
end is the gravitation.
Sorry, I can't hear you. Everybody's trying to talk at the same time. Yes.
So this end is the FG. And is this small?
What N? The
I
N.
mean,
That's
this
newtons.
force. Yeah, I mean, this number
That number
is
is
for FG. Is this?
That's right.
the force between.
That's right. Yeah, yeah, yeah. You're not going to have a measurable force between two small objects, okay? In order to have measurable force, we need, like, massive, massive, massive objects.
So there is actually a tiny force reacting to each other.
Yeah, we're tracking.
Even we're not touching. Yeah. So technically, we're all touching.
No, we're all attracted to each other.
We're all attracted to each other. But no, we are. I mean, technically, there's, if you want to get more technical, there's the exchange of gravitons between all of us. So yes, we are
Wait, exchange of graviton?
gravitons, the force carrying part of
Okay,
it.
at the beginning of the
Yeah,
year,
yeah.
there's kind of like gluons. Now there's gravitons. Like,
Yeah.
Wait, so there's lines between like me and Tom.
1 at a time. And Jordan's gonna turn around. Great. Rob.
Gravitron's theoretical. Or they-
There's no R. Gravitron is the cool ride at in a lot of different theme parks. Yeah. They are theoretical. They haven't been experimentally verified yet.
So there's even like a small amount of gravitons between like me and Tom, like me and
like,
Josh even.
like the power.
Between you and Alien Bob on planet Zoltar. Yes. Yeah. There's a small amount of gravitons. It's gravity is a universal
Oh,
force.
that one starts reacting.
Yeah. Okay.
5 seconds later, towards
I wonder if I can make this.
Maybe I can follow my graviton and pick.
Do we have universal constants in our textbook? I forget these values all the time.
I don't think so.
I think
Then it should be the back of the textbook.
Oh, no, that's actually-
Don't worry.
No, the very, very back, like the back.
He's like,
Yeah, we do.
Eh,
what rank is he?
No, we don't.
Oh, sorry. Slipper slip.
Mass of the Earth.
Oh,
No, I got it. I'm just gonna pause this.
Probably a
Let's
force.
go to some-
Okay, guys, quiet, please. I've got these. Got the values.
I don't think you can. What?
Okay, the radius of the Earth was 6.38 times 10 to the 6 meters. Okay. So this time we're going to see how little g is equal to, is derived experimentally from the mass and radius of the Earth.
Yeah.
Okay, so we're calculating the force of gravity 2 different ways here. So all we have to do is plug in the proper values on the left, right-hand side.
Wait.
Because you could say, because G equals FG, because the G equals FG. There's like
What are
really
you
big
thinking
numbers
numbers
for FG.
I forgot I put age. Wait a minute. How does all-
And again, this is where the calculator work gets tough. Okay, this is where you gotta be aware of the brackets. We're having a nice visual display on your calculator is awesome.
Yeah, my
I
calculator
got-
is
Yep.
awful. Like, actually.
I got 9.7.
Wait, gotta verify that.
Yeah, you're not gonna get exactly the right
Yeah.
answer.
The thing. Like I can't use it in the dark.
I'll just put 9.8.
I am going to verify that.
I don't think we can do that.
Just see
What's
what
how this is solar power and it's using less than
No, because I've done the power of 6.
9.7827.
We'll just leave that. We'll round it to 9.8.
But it's,
Why are you gonna throw that at
but the thing is, that's 3 significant.
Oh, that's what I got it wrong.
Why don't we stay at 3 then?
Apparently not.
I will tell you why.
The alternative?
Okay.
Wait.
No, it's the reason you don't get exactly 9.81 is because the it's not actually okay. The core's material is different than the mantle's material is different than the crust material on the surface of the Earth. So because the crust is a this is what I was told anyways. I don't really understand it because crust is less dense, so we should be actually using a lower number than what we just calculated. But anyhow, for some reason or other, the fluctuations based on the gravitational field from the crust creates a slightly different value than what you'd calculate if you actually use the values of the radius and the mass of the Earth.
Oh.
I don't know why, but that's what it was explained to me. Anyways, with two significant figures, it rounds to 9.8. Which is close enough for me. That's good enough.
Well, we always round it to 10, so.
Yeah, and then yeah. And then IB turns around and rounds it to 10, so it's even better. Okay, example 3.
Here we go, guys.
That's fun.
Whoa.
This time we're going to the moon. So we got the mass of the moon, we've got a 65 kilogram person, and we've got the force of gravity acting on that person on the moon.
We
Calculator.
need to swap out the radius. Armstrong. The guy's Armstrong.
Yeah, that's right.
So F equals mg then?
Yeah. No, F equals mg.
Yeah.
No.
Oh, what?
Remember, little g is just for Earth.
F equals,
Oh, right, FG
G.
was mg.
Yeah.
FG was mg.
Oh, G.
Double G. Basically, I'm saying FG was mg.
Little m is the first.
Yeah, that's, oh, sorry, that's right. Whenever they deal with big and little masses, they actually use big M and little m instead of M1 and M2.
Why are there so many signatures?
Why not?
No.
Wait, how come the Earth only weighs like 2 extra zeros?
That's
That's
times
a
that's
lot.
100 times.
That's a lot. Yeah.
Yeah, okay.
Especially when you're up.
G and solving the radius.
Nick! Josh, you getting flustered over there? Wait, we're assuming that the gravitational universe, gravitational Hawkins universe,
That's so huge. Yeah, that G is used for
everything.
everything.
Oh,
Any two masses.
okay,
That's the whole point of this.
That guy got lucky. What was his name?
All right, so we can. Oops. Forgot to square it on that. So we can do a little cross multiplication and then square root.
What was G? Big M
What number is this? 1? 1 million. 1
Are we
million
finding the radius?
Seven
Oh, no, wait,
hundred
finding
and
the G.
50,000 318.364, and I assume that's in meter.
Dude, don't forget to round.
I know, is that meter?
Yeah.
1 million meter.
So huge.
So that.
I know, right? These numbers are too big to like. 6.67.
So 1.75 times 10 to the power of 1.
Yeah, I'm kind of doing it on my calculator. My calculator doesn't also.
1.75 times 10 to the power of 6 meters.
I need a new calculator, absolutely.
Yeah, I got
Actually,
1.75 million.
This one's McMaster.
0.75 times 50.
Yeah.
I'm on
What?
the Chinese version that yours.
1.75 times 50.
Mine's 25. I got it right?
6.
6.
Hey.
Hey.
Nice.
You got that.
What's big?
How did I mess that up?
Oh, it's negative 11. I put
Yeah, now compare that to the Earth, and
So tiny here.
The force.
so it's about 3.6. The Earth is about 3.6 times the radius of the Moon.
Which is a conversion rate between kilometers an hour.
No, jeez. That's
Oh,
not. That's
stop.
nothing to do with it.
It's like mind effing you. It's like randomly just like say random stuff.
All right. This question, I guarantee you're not going to put at the bottom of the page.
Hey, are we gonna do it then?
We are going to do it. 'Cause it's a really good question. But you're gonna need. You can start it there, but you're gonna need to probably continue it somewhere else.
No.
Between the Earth and what? Let's go with the star.
It says
Okay.
I really believe this says the IV.
Because that's like the point where the Earth's gravity and the Moon's
This is the
gravity
guy who built potatoes.
is not acting on like.
Did you build it or did you buy it?
No, I built it.
And he failed on the first try.
There you go.
I was studying bio. I was so frustrated, and I saw the video, and it made my day.
That's good.
Mr. King Gursky.
Yes.
But what would it be like? Being
So let the middle
like
go.
exactly that spot where the
Nothing. You'd have no force pulling on it.
Like,
Miche, there's going to be nothing, no sound,
Yeah.
no light, because the sun doesn't exist. Extremely cold,
You're frozen.
and you're probably dead.
Okay.
You're probably going to die.
Let's say you're in a spaceship, right? Like you're in a spaceship and you're exactly that far away from between the Earth and the Moon.
And Jupiter's gonna put it on.
Nothing is going to happen.
Like-
Darth Vader don't exist.
So you just stay there. You just.
Yes, he does.
How many are
In the
there?
galaxy.
Long time ago.
That doesn't
Keep
mean
that
in
in
a
mind.
galaxy far, far away.
How many Darth Vaders
And a long
are
time
there?
ago.
Yeah.
It says where the force of
Darth
gravity
Vader.
will be equal to the force of gravity.
Oh, so there's more than one.
Equal to and opposite. So.
That's right.
What do you mean?
Just the magnitudes are gonna be the same.
Vader.
Yeah.
Does it have to be the radius of the Earth?
How do we know
The radius of the moon
Darth
D2?
Yeah.
We're going from the
It's
middle.
like Darth Vader. The Darth Maul.
We're going from the middle of the Earth to the middle.
Oh,
of the Moon.
literally. Oh,
Yeah.
There's the chance.
Different color here.
Oh, no, it is.
What do you mean chicks? Stupid chicks.
Bisexual was sit forward thing.
Michael's listening to her. And Michael's
No, they look so ugly.
Okay. Quiet. Alright. If we use D1 and D2, I feel like I've got drawn on the board here, and I'll upload the picture of this to the internet, then we have too many variables, Jorah. We have too many variables. Okay, we can't solve for D1 and D2 in one equation. But if we know the total distance from the Earth to the Moon, we can. Colors here.
Do we need to round that to sig as well?
We'll call this D total.
That is equal to 384,300.
That's right. So we can say D1 is equal to D total minus D2.
put 6.67.
Warhound? You know what? Let's make it yes, because it was so needed to get out.
Times the mass of the Earth.
Next line, we can do some simplification. Two variables that we can get rid of. Little m and
Big G.
g. Good. And to make our lives easier, we're going to take the two terms that have a square on them, and we're going to bring them on the same side of the equation. So I'm going to cross multiply the bottom left to the top right, and I'm going to take the m of the mass of the moon and bring it down to the bottom left. So we're left with
Isn't that so much? So much easier.
the reason that I did that is to avoid having to do a FOIL expansion and then collect like terms and all this
Oh, I
stuff.
hate doing that.
Because now that I've got both square terms on the right hand side, I can just square root both sides. Square root both sides. Yeah. Okay, so
That sounds so much fun. It's gonna suck a lot.
I hate like.
let's keep going.
Why don't we just plug in the number now?
Sure. Get me a number for the left hand side.
Yeah.
So, yeah, get me a number for the left hand side, and we'll start
What's the
canceling things
mass
out.
of the-
Can we?
So square root of the mass of the Earth divided by the mass of the Moon. Let's plug that in on the left hand side.
Where did you get those numbers from?
Mass of the Earth is up here.
We calculated it earlier.
The information very mental.
Mass of the-
Sincerely do not want to put these in.
Oh, no, it's the Moon. Whoops, mass of the Earth. 5.97 times 10 to the 24 divided by 7.349. Oops.
22.
Times 10 to the 22, and then square root
That's 3.
9.
Wait, what did you divide?
I got 3.
Radius of the Earth?
9.01.
I got 9. Yeah, 9.
But then you square root it.
Yeah,
Yeah.
that was square root.
Oh.
I think you square rooted twice. Yeah.
Oh, the root.
Nice.
Not 9.
Oh,
Thanks, Josh.
and the
Thanks for
total
catching up.
distance is,
Did you just say
I'll
1 second?
let's say 3.84
Times 10 to the negative 6.
times 10 to the, hold on.
Oh, 5, sorry. 5.
No. Because that's in kilometers. So we need 3 more zeros, 4, 5, 6, 7, 8. Hold on.
Max,
I suppose that you would know.
Okay, what's the question? Take the mass of the Earth, 2 questions ago,
Okay.
divide it by the mass of the Moon from 1 question ago,
Oh.
and square root it. So in 1 step, it's a lot easier of a question now. Okay, so now I'm going to bring the D2 up to the top left. So we got 9.01 D2 equals 3.84 times 10 to the 8 minus D2. Bring the D2 over to the left again.
So it's 8.01? Oh, wait, it's plus. My bad.
What?
Right. Yeah, 10.01. True.
Yeah, because if you're bringing it over, it's plus.
What's that?
What is D2?
I don't need to know D2.
You don't
That's only 10 point.
Because we're saying that D2 is 1 D2. So I'm just saying we've got
Okay,
negative.
say that again. What is the M?
No, what happened to?
Oh, that was meters. I shouldn't put that in there. That was just the unit.
So, yeah. We have
Here it is on
9.01 D2s plus One D2.
Oh.
So it's 38 million. 3.8 times. Actually, how many
I got
six?
what? 38 million.
38.
3.84 times 10 to the 6.
That's fine.
You sure it's six?
Yeah.
Whoa. Calm down.
7. 7.
True. Yeah. 3.4 times 10 to the 7.
This is good. What is happening? It's glitching on me.
You should work out.
What happened?
Absolutely.
Yeah, because 10.01 is so small, we can just minus
So-
8 minus 1 equals 7.
Yeah, that's right.
Yeah, because it's like 0.
What is happening?
That's Michael. Michael's
It's
the
a-
force.
it's
The
a
force.
representation.
The force.
This is crazy.
Quite a crazy class today.
Click extension.
I
Save
can't.
it. Just save it right now. We're
Yeah.
gonna lose it. Just save it. Yeah, and then close it.
What is D2?
What?
No, it's to the move to the point that we're looking for.
No, it's not. Yeah, and the total distance is 50 power of 8. Total 3.8.
Hey guys, quiet down. Quiet down. Relax. Somehow along the line we solved for the opposite distance, but that's the right value. That would be D1 as I drew it on the board. All right. But that's fine. We're okay with this. It's not a problem.
Wait, what? That would be G1?
Yeah. As I drew it on the board, D1's far bigger than D2, right? So D2 would be would be
Between
3.84 times 10 to the power of 7. Yeah, meters.
Is that the answer?
That's the answer. Yeah. So
From the
Wait, so
moon.
D,
From the
D2
moon.
is smaller?
From the
It's
Earth.
Smaller.
The
bigger.
moon.
No, because then you'd be really close to the Earth.
gravitational force.
What do you mean?
If it was,
You won't. Because you have one digit less than the total distance.
yeah.
You minus that. Like 10,000 minus 1,000, are you closer to
Tom,
the moon or to Earth?
relax.
Is this? Sorry, I was just asking if this is the distance to the Earth.
No, it's just
It's distance from the Earth, 90% of the way between the Earth and the Moon. Okay, so it's about, right about like here. We get really, really close to the Moon is when it would be the equivalent.
Wait, I'm confused.
Why are you confused?
D2. What's D2 supposed to be?
It usually
Same
rates
one.
D2 and D1.
Yeah. I guess the way I've got it drawn here, we'd have to. I'd have to look back at the math. I must have missed a negative at some point, but that's the right answer. And so this would be D2. What's confusing?
well, D1 is
Okay.
bigger than D2 as we come on.
Yeah.
Because
Yeah,
D2
because isn't that it's closer to the moon, right? That point is closer to the moon than to the Earth.
D2 should be bigger than, as I've got it drawn here. Okay. Okay, go ahead.
The total distance, if you take that and then subtract it from the total distance,
Yeah.
you get a bigger number than that.
Therefore, D2 is a
Oh,
smaller number.
okay. Oh my God, that makes so much sense. Okay. I'm having trouble with my scientific notations today. That's where the problem was.
Exactly.
The answer was fine as I had it drawn. Thank you. 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 Okay. Everything's fine. Everything's fine in the physics world. We didn't break physics. Your teacher just couldn't realize that the second number would be larger than the first one.
How many times did we work with physics this year?
A few times.
Not as many times.
No, that's fine. No, that's still okay.
What were being the potato gun?
Yeah, and that's fine. Everything's fine. My interpretation's wrong. That's okay. So that still represents, the way I've drawn it on the board, since D2 is a smaller value, that still represents 90% of the weight of the Earth. Or 90% of the weight of the moon, I mean. Okay?
Except you're using the moon as the standard, not the Earth.
Yeah.
Yeah.
Fair enough?
Well, we finished that. This space.